Okay, so honesty is a very important part of science, so I can't lie to you that today's going to be pretty brutal because you have 2 lectures and a lab from me, and I already know from experience that my knee is only good for 1 lecture. So I'm going to try kneeling on this stool and sitting over there, using Emmanuel's walking stick. And if I don't make it, well, just, somebody else can take over. And if one of you guys burn out your brain or something, well, there's an ambulance standing by down here. So I'm not sure whether this will do more damage to you or to me, but anyway, here's what we're going to do. This is radiative transfer theory class. And radiative transfer theory is just a fancy term for the branch of physics and math that deals with how light is measured and propagated and absorbed and scattered, and all of those things. So what you're going to do today, the goal is that you'll experience the beauty of radiative transfer theory. And I'll start out, I'll give you a few words on scattering of polarized light, just so you can see what a mess it is. You'll understand why there's not a polarized version of hydrolite. The most of it will outline how you get from the very fundamental physics down through the equation that hydrolite solves. And then we'll do a couple of very simple pencil and paper solutions of the radiative transfer equation, one of which is called Garrisons Law, which is very fundamental in its applications. And so we'll see a couple of those things down at the end and just mention a couple of other things. So back to our organization chart, we've done IOPs, we did radiometric variables. Yesterday, I guess it was, we did AOPs. And today we're going to go back and look at this box here, which is the radiative transfer equation, and see where that thing comes from. And then next week, we'll finally talk a little bit about things like the C state and the bottom reflectances and so forth. And then you'll know pretty much everything there is to know about optical oceanography. So, whoops, hang on here. This guy is supposed to be, yeah, there we go. No. Well, let's see here. Hang on. There are some little, well, anyway, it worked in my room last night, but this is if you were looking into, say, the beam of this laser and looking at the electric field, it would be oscillating in some plane, and that's plane irradiance. And anyway, then if you had circularly polarized light and you were looking into the beam as this light comes along this way, you would see the electric field vector rotating in a circle, either clockwise or counterclockwise, depending on whether it's left-handed or right-handed circular polarization. And be forewarned when you read papers, what one person calls left-handed, another paper calls right-handed. And it doesn't matter which one you pick, you just pick it and stick with it. But it makes it very hard to compare papers. And also be forewarned that when people write some paper on polarization and they talk about the perpendicular component or the parallel component that Ken was talking about, well, in our field, when we deal with these meridian planes that I'll talk about in a minute, it would be parallel and perpendicular to those planes. So parallel or perpendicular might be oscillating in the horizontal plane. And then another guy picks parallel and perpendicular to the ocean surfaces. So the mean ocean surface parallel to that would be perpendicular to this. And it just, you can spend an enormous amount of time trying to figure out why 2 different papers or 2 different models just give you different answers. And it's always the case, something like that. Anyway, as Ken mentioned, polarization is defined by what's called the Stokes vector. which has four components, I, Q, U, and V. And I is just the total radiance, what we call L, without regard to its polarization. And Q and U are used to pin down the plane of the plane polarization, wherever plane that field is oscillating in. And V then can either be positive or negative, and that tells you about whether it's left or right circular polarized. So the idea here is just like in unpolarized light, we're going to have an incident Stokes vector S coming at some direction, theta prime, phi prime in my system. And so that's a 4x1 column vector that interacts with the particle and it scatters off into some other direction. And we get a final Stokes vector S theta phi. And so the Stokes vectors are 4x1. There's going to be some kind of something that describes this scattering, and out comes another 4x1 Stokes vector. So that something is going to have to be a 4x4 matrix to get all the dimensions to fit together correctly. And this 4x4 matrix is called the phase matrix, which is a little weird. It's really more like a volume scattering function, but in our world, we call a phase function is like the volume scattering function with the scattering coefficient factored out. Well, it's just a historical name and you have to live through it or live with it. So anyway, we're going to have this 4x4 matrix that takes us from one direction to another, or in terms of a scattering angle psi, which is given by this equation here. Okay, this business of how you pin these things down, we pick our coordinate system and we have our z-axis, which in the ocean is typically positive downward. And we have light propagating in some incident direction given by the red vector here. And then this plane defined by the z-axis and the direction the light is propagating is called a meridian plane. And that comes from the name that when the sun is highest in the sky, that's the meridian, and the plane between the sun and the zenith is then the meridian plane. It's where the name comes from. So then, in order to determine what are the Q and U, I, Q, U, and V values, you have to pin down what am I going to call horizontal versus vertical or parallel versus perpendicular. So typically, people will say, okay, we have the meridian plane, and let's have a direction that will be horizontal or perpendicular to that plane, and one that will be vertical or parallel to the meridian plane. And then I can describe this Stokes vector in this local H prime, V prime coordinate system. So I have it just like an X, Y, Z. I now have an H, V, and R prime going out in the radial direction. And that gives me a little local coordinate system that I can use to write the Stokes vector. Okay, the catch comes that when this light that's going in this direction scatters into some other direction, well, Ken showed you this Mueller matrix, and the Mueller matrix works when you're in what's called the scattering plane, which is the plane determined by the incident and the final direction. So when you actually work with polarization, what you do is you start out and you say, I'm given the Stokes vector and it's described in this meridian plane, but it scatters off into some other direction, which is a different meridian plane. Now that Z matrix takes you from this meridian plane in blue and scatters you over into the final meridian plane, which is in this orangish color. But what you normally do is say, let's separate the geometry from the scattering, from the physics. So they write that the phase matrix, they write as a rotation matrix times Ken's Mueller matrix times another rotation matrix. So what this does is you have the light coming along here, and you apply one matrix, which is a 4x4 matrix, and that takes you from this H prime, V prime system, which is defined by the meridian plane, into things resolve now in S and P, which actually stands for zinc base parallel, which is German for perpendicular and parallel. So you now know the Stokes vector of scattered light, but it's relative to this red scattering plane. And then you have to do another rotation that takes the S and P into a local horizontal and vertical set of axes relative to the final meridian plane. And I can tell you from experience, if you can take this and write a computer program that does all of this correctly in less than 3 months, you're ahead of me. So it's a real mess of figuring out these angles and figuring out all these little rotation matrices and everything. It's just a can of worms. So anyway, what we've done is we've taken our phase matrix, which you can think of as like the big volume scattering function for polarized light, and we turned it into some geometry times some physics times some geometry, and you finally get the last thing there. And if you actually want to see the equations, go to the web book. But that's about all I want to say about polarization. And I'm only saying that because we're going to end up with a radiative transfer equation that works for polarization. So you kind of need to see where it comes from. So anyway, in our world, most of the time, we only care about the total radiance, which is the first element of the Stokes vector. And the reason oceanographers can get away with not dealing with polarization underwater most of the time is that things like phytoplankton photosynthesis or the heating of water, the state of polarization of the light doesn't really matter. If you're a phytoplankton and some light comes along, you grab it, you photosynthesize, you're happy. And you don't care if the light was polarized this way or that way. Likewise, if you're a water molecule. So all you care about is I grab some energy, I heat it up, I'm happy. So we don't really need to keep track of the polarization. Also, as we'll see later on, if I ignore polarization, like in hydrolite, I make an error there. But what'll happen is in this direction, maybe my error is 10% too big. In that direction, the radiance hydrolite computes is 10% too small. But if I'm interested in an irradiance, I integrate all those over all of the directions, and the error is too big here, it's too small here, it's just right there. Those errors all tend to add out. And even though the radiances themselves might be off by 10 or maybe 20% in a particular direction, an irradiance will only be off by, say, 1%. And that's better than you can measure anyway. So we get away with ignoring polarization. On the other hand, by ignoring it, you're also throwing out information. And things like the particle size and shape those determine how polarized light is scattered. So if you actually are measuring polarization, then you have some extra information that will tell you about things like particle size and shape. Are they spherical or are they non-spherical, for example? And so that's why Emmanuel and I and Jeremy and all these people will tell you that polarization is coming in the future. It's just that the people like Mobley are running 20 years behind time in developing models that can predict it underwater. I mean, there are some, but they're not available. The other thing is, even if I have this big fancy radiative transfer equation that fully predicts polarization, you don't have the measured inputs that you need to run it. It's hard enough just to measure the volume scattering function, let alone to measure 15 more things like that fill out that 4x4 matrix. There's just no instruments out there that can do that. So you have to model it. So then what do? Oh, you can use me theory. And well, then you're assuming homogeneous spherical particles, the whole story. So for this class, we ignore polarization most of the time. So then to get on with deriving some equations here, there's two approaches you can take. There's what's called a phenomenological derivation. And phenomenological whatever just means that I'm going to come up with some kind of equation that describes what I'm interested in. And I don't really have to justify where it came from as long as it works and gives me the right answer. And then there's a rigorous or physics-based derivation where you go back to the fundamental physics and you start there and you get the right equation. So if you look in every textbook, including light and water, what they do is they start out, they define this quantity called radiance, and then they look at a beam of light going along. Some of it gets absorbed and some gets scattered out of the beam and some gets scattered into the beam, etc. And you basically make conservation of energy arguments in terms of radiance, and you end up with this scalar radiative transfer equation that hydrolyte solves. And that's the way the field has been until about 10 years ago. And then finally, this fellow, Michael Mischenko, was actually able to start with Maxwell's equations, end up with a very general vector radiative transfer equation, which can then be simplified and get you down to here. And there was always, in radiative transfer theory, it was always looked down upon by the physicists because it was what they call the island of radiative transfer theory that wasn't connected to the mainland of physics. And quite a number of people over the last 100 years had tried to build what Preisendorf would call the bridge between the mainland of physics and the island of radiative transfer theory. And the math and the physics was so complicated that nobody was able to do it until Mischenko and a couple of his coworkers, who finally about 10 years ago showed how to start with Maxwell's equations and end up with what we want. So now radiative transfer theory is a full-blown legitimate subset of physics. Okay, so the whole process, and you're the fourth group of people in the world that has seen this. The previous class I taught in China, class I taught in Korea, and now this class to outline what really happens here in a way now that keeps the physicists happy. And so you start out with what's called quantum electrodynamics, which is a very fundamental physics. We think it's how light really does work. And the problem is it's incredibly complicated and abstract. The only calculations you can do with QED are things like elementary particles interacting with each other. And even if you have something like 2 electrons come in, they scatter off of each other, they go away, it can take a year of computer time to compute that interaction using QED. On the other hand, you get predictions that agree with experiment to 1 part in 10 to the 12th. And that's the equivalent of measuring the circumference of the Earth to within 0.04 of a millimeter. It's phenomenal accuracy. So that's why we think now that QED really does give us the correct description of how light interacts and how charged particles interact and all of that. The problem is there were multiple Nobel Prizes given out for developing this, and you can go from QED to Maxwell's equations, which is another Nobel Prize level of difficulty. And then you can go from Maxwell's equation to a radiative transfer equation, which was only worked out by Mischenko about 10 years ago. And so we're going to pick up here and then do these simplifications, and you'll see how that goes. Okay, if you want to read a little bit about QED, there's this nice little introductory book here. There's more about it on the website. So you can follow that with that if you want, but you don't need to know it as an oceanographer. Okay, light's really a bunch of particles, these photons. And as this guy here, another Nobel Prize winner, says, that when you have zillions and zillions of photons, and we're talking about like 10 to the 20th, then you can kind of start treating the light field as though it was sort of like a continuous variable, not a little bunch of little particles. It's just like if you have a liter of water, you can treat it like a continuous fluid. You don't have to think of it as being a bunch of water molecules. And then you get into the world of electric and magnetic fields rather than individual photons. And so you get out of this, you then get Maxwell's equations. And Maxwell's equations describe electric and magnetic fields. And they work perfectly well for all kinds of everyday problems. So if you're going to build an electric generating plant, if you're going to build an electric motor, if you're going to build a computer, if you're going to run these lights here, you start with Maxwell's equations, figure out what's going on, and away you go. So they're perfectly good for everyday life. They could be used for oceanography, except they're still so complicated that it's just not worth trying to do the math, even with the biggest computers. And they rarely get used in oceanography, although the very first paper that did calculations in optical oceanography actually started with Maxwell's equations back in the 20s, all pencil and paper, of course. Okay, so just keep in mind, Maxwell's equations are correct, but they're still too complicated for oceanographers. But out of Maxwell's equation, you finally can come up with the first thing we would call a radiative transfer equation. So here's our Stokes vector. Here's our phase matrix. We could have an internal source. If I put this laser in the water and it shines out polarized light, well, I'm going to have a source term to describe that. And then phase matrix, here's another matrix K, which is called the extinction matrix, and it's multiplying the Stokes vector. And then this C dot grad S, that's really a bunch of spatial derivatives that if you've had advanced calculus, you know what those are, and if you haven't, don't worry about it. But the bottom line is that K is a 4x4 matrix that's multiplying the 4x1 Stokes vector, and it describes how light is attenuated as the light goes through the water. Now, in general, if you have a crystal, for example, and crystals have a spatial structure that's different in one direction than it is in the other one, if you shine light through a crystal, it may attenuate at a different rate if it's this polarization versus this one, and that's called dichroism. And or you may have a medium that will propagate left circular different than it propagates right circular. So in general, this K matrix is a 4x4 matrix, and all of the terms are non-zero. And then the phase matrix here, it once again has 16 terms, and in general, they're all non-zero. And what those different terms do is they say, well, if I have light that's polarized vertically, how would it be scattered into horizontal polarization? Or if it's polarized vertically, how would it get scattered into left circular or right circular? Or if it's at a 45 degrees angle, how would it get scattered into this direction and so on? So that's what those 16 terms do. And the first term, the 1,1 element, says how is unpolarized light scattered into unpolarized light? And that's what we're really interested in. Okay, so in general, you can use this equation. If you give me the inputs, I can now finally solve this, and I can predict how light would propagate through a crystal. Or a cirrus cloud where you have lots of little ice particles and they're not randomly oriented. So you get weird things, these halos and sundogs and all of this. Those are coming out of this equation. So the atmospheric people may worry about that. We never do in the ocean because we don't have usually things like ice crystals that are not randomly oriented floating around in the water. Okay, so we still need to simplify this equation to get something that's useful for oceanography. And this is where biology comes in. So it turns out that if you're scattering particles here have what's called mirror symmetry, then things get simpler. So what's mirror symmetry? Well, here's a little phytoplankton, for example, and this dotted line is a mirror. So you reflect the little phytoplankton or mineral particle in the mirror, and it's kind of, reverses left to right as it looks like. And then if you can take a particle, reflect it in a mirror, and then rotate it, and it looks like the particle you started with, that's called a mirror symmetric particle. Now here's another little particle. So that's a little phytoplankton. He's got a little head here. You reflect him in the mirror, it looks like this. And now you rotate this guy. Well, the head's on the wrong end. So this thing does not look like this one, whereas this one looks like this one. So this is not a mirror symmetric particle. So now the question is, do the particles like phytoplankton and mineral particles that we have in the ocean, are they mirror symmetric? Well, here's a bunch of diatoms. So every one of these guys, if you pick a plane somewhere, so for example, this guy, if you pick a plane like through there and flip this guy in the mirror, then this little triangle would flip that way and it still just look like a triangle. Or if you picked, say this one here, you could, whoops, done it now. You could pick a plane like this and flip it through a mirror, it would look the same before. Or you could pick a plane this way and flip it through a mirror and this guy would look the same. So those are all mirror symmetric particles. You know, this one here, weird looking thing, pick a plane through the middle that way and flip it left to right, he still looks the same. So it's a pretty good assumption that phytoplankton and other little particles, mineral particles, bubbles, whatever, that they do display mirror symmetry. So we're in luck. Now, not all phytoplankton are mirror symmetric. So here's this cute little guy here. He's this helical thing, and that's either a right-handed or a left-handed helix, depending on how you want to define it. So if you flip this guy in the mirror, the right-handed phytoplankton looks like the left-handed one. So this does not have mirror symmetry. So if you were really wanting to model phytoplankton or model light propagating in a bloom of these things, where these were the dominant particles, you'd have to go back and use that full-blown equation. But 99 times out of 100, you don't have a bloom of these things. The particles are mirror symmetric, and you're okay. So when you do have mirror symmetric particles, what happens is that 4x4 attenuation matrix becomes diagonal, and the diagonal values are, guess what? The beam C coefficient, the beam attenuation. So previously, the different states of polarization could attenuate at different rates, depending on their state of polarization. But if you have mirror symmetric particles, then all states of polarization decay at the same rate according to the same beam attenuation coefficient. And then for mirror symmetric particles, this 4x4 Mueller matrix looks like this. There's a little block of 2x2 here and 2x2 here. These two are equal, and these two are equal, except the sign is different. So there's really 1, 2, 3, 4, 5, 6 independent elements. So you could measure these 6 elements here, and then you'd have what you need to do full-blown radiative transfer calculations. Okay, so what does, if we go back, what does this thing actually look like measured in the ocean? Well, Ken showed you this. It's from his PhD dissertation way back in the dark ages of the field in '84, and still the best data that's out there, that's the most widely cited. So what he's done and what's common is you take the full matrix and you factor out the 1-1 component. So this becomes a 1 here, or actually an identity matrix, no, sorry, a 1. Then this becomes M12 over M11, M22 over M11. So you just pull out this term, and what's left is called the reduced Mueller matrix. And the M11 term here, that's our volume scattering function in our world. Okay, so Ken has factored out the M11. So the first element here is just 1s, and then the M12 divided by the M11 element, well, that looks like this, and there's the M22, and so on. So a few little things, if you do all the physics, for example, if M22 is not equal to M11, that tells you you have some non-spherical particles. For spherical particles, this element and this element should be identical. Well, in Ken's data here, they're close, but they're not quite identical. So you're getting a little bit of effect of spherical particles, for example. And then notice that the M12 and 21 those are equal to within measurement error. So there's really only one independent thing there. And this guy and this guy, those look pretty much equal. Both of those look like they're zero. So there's really only kind of the M11 is 1, 2, 3 things, maybe 4 you need to measure in order to fully describe the Mueller matrix for typical ocean phytoplankton. And so people are now starting to do that. And Sequoia makes a version of the LIST instrument that actually measures the first guy, and then it measures the M11 and the M22 elements. Doesn't measure these, I don't believe. So anyway, people are starting to have instruments that make those measurements, so we could do polarized calculations in support of the coming instruments like PACE, which will have polarized radiometers on board. Okay, so enough said there. Now, the next simplification is to say, let's just make the ocean horizontally homogeneous. So every point's the same on the surface and going down, but things can vary with depth. And then this left-hand side of the equation just becomes cosine theta d Stokes vector d depth here. So a depth derivative. And then you end up with a one-dimensional, one spatial dimension, vector radiative transfer equation for mirror symmetric medium. And it looks like this. So we've got a depth derivative of the Stokes, we've got beam attenuation, and then we have these rotation matrices, which you know, and then a Mueller matrix, which looks like this. And these rotation matrices actually have this sort of form here, if you know the angles. So we're now in business. We can solve this equation, and the atmospheric community typically works with this equation. Okay. What we care about, though, is really the unpolarized light, which is just the first element of the Stokes vector. So if we write this equation out for the first element, so we're going to have cosine theta d radians dz equals minus c times radians, and then we pick out the components of these matrix multiplications that only involve what we're interested in, you get an equation that looks like this. So here's this part, here's the M11 element, which is the volume scattering function, times the radiance, first element, and there could be a source term that's putting unpolarized light into the water. But then the other parts of the matrix give you these two terms that involve the M12 elements, and then there's the Q and UV components, which are describing the plane polarized light. So I only care about the unpolarized light, but I can't predict that unless I know the state of polarization, so I can evaluate those terms. So I'm kind of in a predicament that I don't want to solve the full polarized equation or the full vector equation. I just want something I can get the unpolarized part, but I can't get the unpolarized part unless I solve the full polarized or vector equation. So what do? Well, you either go back and you work with the full Stokes vector business, or you say, I can't evaluate these terms. Let's just throw them out and hope for the best. And that's what happens. Now, these terms, of course, are telling you how the horizontal and vertical polarized light is scattered into unpolarized light. So that's what they're doing. And so if I knew, for example, that my light field was unpolarized, well, then the Q and U would be zeros. But of course, in general, the light field underwater does have some linear polarization. So you're faced with this problem. And so all you can do is say, like I said, let's ignore these terms and hope it doesn't make too big of an error. Now, what we can do here now is an error analysis, because if you go back, if you look at this M12 term, okay, it's zero at zero scattering angle, 180 degrees, and it looks like it's maybe minus 0.8 or something like that at 90 degrees. So if we go back, whoops, sorry, wrong direction. If we now go and, well, here's a little aside, I'll come back to that in a minute. If we throw those terms out, so we just go here and we say, forget this term, we end up with this equation right here, which is an equation for the unpolarized light in terms of, now I've replaced M11 by the volume scattering function, that's what we call it. I replaced I by L because that's what we call it. And we have a nice equation now that I can have some hope of solving. And that's the equation that hydrolyte solves. Now to back up here, there are now, as I said, some instruments that measure some of these elements of the Mueller matrix. And you know, there's some references there to the latest ones. I think Slade one describes Sequoia's instrument, and a couple of other people like Mike Brodowski also have instruments that can measure some of these elements of the Mueller matrix. Okay, enough said there. So we drop those terms and say, forget it. We get something we can solve and we go ahead. So how big of an error does that make? Well, if we go back to here, we've got a term that's basically M11 times I, and then we have terms that are basically M12 times Q or M12 times U. So, and then everything else here is the same, I mean, except for these cosine angles. But basically, if we can compare how big a magnitude is M12 times Q compared to M11 times I can get some idea of how big the error is. So if I do that, I go back to Ken's data and I say, well, M12 is at most about 0.8 at the 90-degree scattering angle. And the M11 then is, that's 0.8 is relative to M11. So M12 over M11 could be as much as 0.8, usually less, but at 90 degrees, maybe 0.8. And then measurements of underwater light fields show that, oh, they can be as much as maybe 30% linearly polarized, now often less, but something like that. So we do a worst case scenario and say, well, if Q over I is 0.3, so 30% linear polarization, then we would have something like 0.25 for this ratio. So that would say at a 90-degree scattering angle, I might be off by as much as 25%. Now, near forward scattering or near back scattering, no error at all because M12 is 0, and something in between for all the other directions. So I at least have some gut feeling that if I ignore those polarization terms, I might be off by 10% or 15 or whatever, and maybe sometimes by as much as 25%. But in one direction, it would be 25% too big, another direction, 25% too small. I computed irradiance, those average out. So I can now do this kind of error analysis by doing the rigorous physics approach, which you can't do if you do the old phenomenological theory. You don't know how big your errors might be. So enough said on that. We now have this guy, which is called the scalar radiative transfer equation. Scalar because it's just L, it's not the Stokes vector. And so away we go. Now, I'm willing to live with a little bit of inaccuracy here because I can measure the inputs beam attenuation. I can measure the volume scattering function, even if people don't do it very often. The math needed to solve the scalar equation is enormously easier than the math needed to solve the full vector equation. And the output is accurate enough for most applications, although not all of them. And there are particular instances, if you're interested in the polarized underwater light field, you have to work with the full vector equation. But most people don't do that. And there's commercial software available, namely Hydrolite, for solving the scalar equation. There's no corresponding software that you can get your hands on for solving the vector equation. Some people do have vector codes, but they're proprietary and they're not going to give them to you because that's the source of their funding, is to say, hey, I have a vector code, and so you fund me instead of Mobley. So fair enough. And I worked out the hydrolyte uses a mathematical technique called invariant embedding theory to solve the scalar equation. And I worked out invariant embedding theory for the vector equation and published that. And it was my first paper that was an only paper and last paper that was 100 pages long. It's 100 pages of equations. It's just horrible. And it literally took me months of sitting at the kitchen table, and I took these big pieces of paper like this, writing on it with a normal pencil, and I would fill the whole piece of paper with one equation, line after line after line. And that's what it took to work out invariant embedding theory for the vector equation. And at this point, I said, I'm done. You know, one of you guys can program that up and make a polarized version of hydrolyte, but it's not going to be me. Okay, so anyway, we've kind of seen the physics derivation here and getting to where we want to be. Now, as I mentioned, there's this phenomenological derivation where you think of a little bit of water, light propagates through it, some scatters out, some absorbed. That's what's in every textbook. Colin kind of went through that early on, and you get the right answer, but you kind of got it by the wrong reason, because it's physically not quite correct because you're ignoring polarization. And on the other hand, it works quite well, and you do get the scalar equation, but of course you don't get any error analysis, which is another important thing of the derivation I just showed you. Okay, so we end up with this equation, and what's going to happen is you're going to put in the green stuff, which is beam attenuation and volume scattering function, or something equivalent, and you're going to put in a source term, which might describe bioluminescence, for example, and you're going to solve for the red stuff, which is namely the radiance distribution. So that's how it all works. That's our equation. And this is what's called, it's a linear equation, meaning L is there only to the first power. There's no L squareds. It's a first order equation. There's only a first derivative. There's no second derivative of radiance, for example. And it's an integral differential equation. There's an integral of what you're interested in, and there's a derivative of what you're interested in, the radiance. And so it's to be solved as what's called the two-point boundary value problem. So we've got our water here, and we have sunlight coming in at the surface, and that tells us what the radiance is up here. So that's one boundary. And the other boundary is at the bottom of the ocean, which either might be finite depth with some reflectance, or it might be infinitely deep. So anyway, you have to tell me what's going on at the bottom, what's going on at the surface. That's our two boundary points. And in between, we have this equation that governs how light propagates around inside the water. Now, it's a different story, but in general, two-point boundary value problems do not have solutions. But this particular two-point boundary problem does have a solution. And how do I know that? I know before I play with the math, I'm going to be able to find a solution. Trick question. It's because light propagates through water. If this two-point boundary value problem didn't have a solution, light wouldn't propagate through water. So I have some encouragement to do the math until I finally find the solution, which I know exists. Okay, so in general, to find a solution to the radiative transfer equation, you have some region of interest where you know the IOPs, and you have a boundary, and you have specified the radiance onto that boundary from outside. And then you have a unique solution. And of course, in general, that's a 3D problem. You know, this could be a cloud, for example. What hydrolyte does is it takes The 3D problem stretches everything out horizontally. It's a 1D problem where now we know the IOPs as a function of depth. We know the incident light from the sun or the moon, whatever it happens to be. That's the same at every point of the surface. And we have some bottom boundary here, which is the same at every point horizontally. And then we have a 1D problem. Okay, so let's solve this equation with a pencil and paper. So if we assume the water is homogeneous, assume there's no scattering, so the body of scattering function is 0. It's infinitely deep water, so there's no radiance coming up from the bottom. So that means the radiance needs to go to 0 as the depth goes to infinity. And we have specified the incident radiance just below the sea surface to make it interesting. Well, we go back to the SRTE here. We say no scattering, that means this term is 0. There's no internal sources, that's 0. If there's no scattering, then C, which is equal to A plus B, is just A. So we just end up with this equation with absorption instead of beam attenuation. And there it is. And then we can solve this, divide through by L, integrate from the surface, whatever the radius is at the surface, down to some depth. A is constant, the angles, whatever angle we're interested in, that's constant. And you just get that L at depth in this particular direction is equal to L at the surface in that particular direction, e to the minus absorption coefficient over cosine theta times the depth. So there's Beer's law obtained from the radiative transfer equation. Okay, now a little more important solution here is Garrisons law. So I'll walk you through how that works. We start out with the source-free, one-dimensional scalar radiative transfer equation. And believe me, I never thought as a postdoc that I would make my entire career solving that equation time after time after time, millions of solutions. But what's different is each solution gives a different answer because I put in different IOPs and different boundary conditions. So it's kind of a weird thing that you spend your whole career just resolving the same equation over and over again. Well, anyway, worked for me, it could work for you. We start out with this equation. We're interested in one particular direction, theta phi, at one wavelength, and here we are as a function of depth. So integrate over all directions. So I'm going to just take this whole equation and integrate over theta and phi, theta going 0 to pi and phi going 0 to 2 pi, and see what happens. Well, the left-hand side here, we have our cosine theta dl dz times integral over theta and phi. There's our element of solid angle. And so we write that. Now, the depth derivative and the integrals over direction, those are independent. So I can actually pull the derivative out or move the integrations in so that they work on the things that depend on direction here. And then I end up with the depth derivative of the integral of L times the cosine theta integrated over all the solid angles. Well, what's the integral of L times cosine theta? That's planar radians. So when I'm going from theta equals 0 to pi over 2, cosine's positive, and that's the integral of radians times cosine integrated over the 2 pi radians. That's just ED. Now, when theta goes, if I'm measuring theta from 0 straight down, because it picks my z-axis going down like oceanographers do, then from here to 90, cosine's positive. From 90 to 180, the cosine's negative. So it's actually cosine becomes negative, but we still have the integral of radians times cosine. Well, that's just gives me minus EU. So this is called the net plane irradiance, or net downward plane irradiance. So I end up with the left-hand side becomes the depth derivative of the difference in ED and EU. So, okay, tuck that aside. Go to the next term, the minus CL term. So we're going to integrate that guy over all directions. Well, C is not a function of direction, so that can come out. And then I have an integral of radiance over solid angle over the whole sphere of direction. What's that? That's just the definition of scalar radiance. So that term just becomes minus the attenuation times d0. Then the elastic scattering path function here. Well, we have L times body scattering function going from an incident direction to a final direction, integrated over all the incident directions. And then we're going to integrate that whole mess over all output directions. And at this point, most people would say, I'm out of here. This is why I became a banker or an attorney and not an oceanographer. But it really turns out to be quite easy. So this thing depends on theta prime and phi prime. This depends on both. So I can say, let's bring this integration over theta to phi inside here, and it's not going to affect this guy because that's integrated over the incident direction. And we can basically switch the order of integration, integrating over theta prime phi prime to theta phi, to integrating over theta phi, and then theta prime phi prime. So the theta phi interval comes in here and integrates the volume scattering function over all the output directions for a given input direction or unscattered direction. Well, what's that? That's just the definition of the scattering coefficient. So that's going to depend on depth, but that's just scattering coefficient. It can come outside this interval, and I'm left with an interval of the radiance over all directions, which once again, that's just the scalar radiance. So this whole big horrible mess actually turned out to be very simple. All right, so collect all the pieces then. We end up with this equation, the left-hand side, the first term on the right, the second term on the right, and C is equal to A plus B. So this becomes minus A B0 plus, or minus B0 plus B0. The scattering terms cancel out, and we can actually solve for the absorption coefficient, because this term here just becomes minus A B0. So the absorption coefficient is 1 over the scalar radiance times the depth derivative of dE minus dU. And that's Garrisons Law, derived by this Russian fellow back in the 1920s. And he's probably the first guy who tried to connect radiative transfer theory back to physics, and he failed, and Preisendorfer failed, and Mischenko finally was able to do it. Well, anyway, Ken Boss says a paper back in '89 where he didn't measure these things individually. He measured the whole radiance distribution with this contraption he has, which was called RADS at the time, radiance distribution camera. It's a big thing with fisheye lenses on and all that. So he measured the full radiance distribution, then computed the irradiances from the radiance distribution, plugged in the numbers, compared it with the measured absorption, and guess what? It worked quite well. So it's a very nice paper back from '89. So that's Garrisons Law, and it's an example of what gets called an explicit inverse problem or equation. So in the forward modeling, you start out with IOPs and you predict light fields. In the inverse modeling, you start out with the light field and you end up with IOPs. So this, you start out with measurements of the light field and recover an IOP, the absorption coefficient. And it's explicit because it's a nice simple little formula as opposed to some iterative technique where what you do is you solve a lot of direct or forward problems and hope you eventually converge on the answer to the inverse problem. Okay, so where does this guy get used? Well, if you're going to have an ecosystem model, you need to both heat water and grow phytoplankton. So the first law of thermodynamics says I'm going to heat water. So T is temperature, big T is temperature, little t is time. So this is the rate of change of temperature with respect to time at some depth and some wavelength. Well, you go dig out your freshman physics book and you find this first law of thermodynamics, otherwise known as conservation of energy. And it says, what I need is how much light is there and how much of that is absorbed. And then there's some factors here, the specific heat of water and the density of water. It basically takes this and converts it into a time rate of change of temperature. Well, A times E0, that's just the difference in EV minus EU, the depth derivative, out of Garrisons Law. So Garrisons Law is the basis of all of the heating of water and everything else that goes on inside coupled ocean ecosystem models where you have physics and biology. And then, of course, this is one wavelength. So what people do is they integrate from 400 to 1,000 nanometers, and that world calls that the short wave radiation. Long wave radiation means longer than 1,000 nanometers. So you actually have a similar thing, but it's now not at one wavelength, it's the broadband values. And then you have the rate of change of water temperature due to short wave radiation is the depth derivative of ED minus EU. And then they say, well, you know, EU is usually only a couple of percent of ED. So let's just throw that out. And then they go back to a lecture before and say, I have a model for KD that I can plug in chlorophyll, for example, or I can know it at one wavelength and compute it at the other wavelengths. So I'll use my model for KD to predict ED as a function of depth, and then I can compute this derivative and eventually heat the water. And that's exactly what's done, even in the most sophisticated of global ocean circulation models. It all goes back to Garrisons Law. Okay, then there's some fancier approximate analytic solutions that I'll just mention, but we're not going to dig into the math, but I'll show you how it works. So there's a thing called the successive order of scattering approximation, which gives you a single scattering approximation, which gives you a quasi-single scattering approximation. And when you read the papers, especially ones by people like Howard Gordon, they throw these terms around and they'll just say, well, the QSSA solution is, and they write down some equation, and it's only like 20 pages of paper to get from the radiative transfer equation to that solution, but they assume you know how to do that. So what they do, for example, is again, assume the water is homogeneous, there's no internal sources, the sea surface is level, the sun is a point source in the black sky, and the water is infinitely deep. So you make a lot of assumptions to simplify the equation. And so if we, and also they usually work with optical depth, which is the attenuation times the physical depth. So you have an equation like this, and then they say, let's write this, the radiance as unscattered radiance plus radiance that's been scattered once, plus light that's been scattered twice, and so on. And this omega naught is a measure of how strongly the light is scattered. I call it, sometimes called the probability of photon survival. So it's B over C. So if B is 0, there's no scattering, the light is absorbed. That would make omega naught 0, and you would only have an unscattered B. If omega is 0.1, then you have unscattered light plus a little bit of scattered light scattered once, but then omega naught 0.1, here it's 0.01. So you have this tiny little bit of light that's been scattered twice and so on. So you take this equation, you stick this in here, and that gives you a series of terms for unscattered, singly scattered, scattered twice, and so on. And then you can just rewrite that equation And it looks like this. And then you say, remembering from your undergraduate differential equations course, that, well, this equation has to hold for any value at omega naught. So let's just set omega naught equal to 0. Well, that knocks out all of these terms, and we just have this guy left, which is just going to give us Beer's law. And then you say, well, okay, I know this term, and this all has to eventually add up to 0 for any value of omega naught. So for non-zero omega naughts, now that means that each of these terms in the brackets has to be 0. Otherwise, all of this stuff wouldn't add up to 0. So then you say, gee, I actually have a series of equations. I've got this one, I have this one here, and then I have this one here, and each of those terms, or each of these terms has to be 0, and away I go. So what this technique does then is it simply takes the first equation, solves that, gets L0, uses L0 in here, and notice because of this multiplication by omega naught, that this term that's being integrated is always one less than the thing, or one order of scattering less than what we're solving for. So what you're seeing here is that unscattered light is being scattered to create light that was scattered once. And then light that was scattered once is being scattered again to create light that was scattered twice. So that's the physics of what's going on. So you can solve these equations one by one. Whoops. So the first one here, this guy just gives us Beer's law, slightly different form here. I've written in terms of optical depth and mu is cosine theta, but there's our friend Beer's law. And we're going to have some boundary conditions, which will say at depth of 0, I have the value at the surface, which you know, and then as zeta goes to infinity, the eta minus mu goes to infinity, and so this goes to 0, so satisfies the boundary conditions. And I'm going to now take that solution and stick it in here, take whatever the volume, the space function was, and then I can do this integration, and then I can solve this equation. Well, the math there gets a little messy, and it's actually a full lecture just to solve this equation, but that's what's called the single scattering approximation. So you eventually get an equation that says single scattered light equals, and it's in terms of all the boundary conditions and the phase function and so forth. We're not going to go into that. It's all in the web book. But how well does that solution work? Well, here we are, omega naught is 0.01, and I'm looking at L, what they call that there, L upward and L downward. So here's the downwelling gradients, and here's the upwelling. And then the solid curve is the approximation, and the dotted curve, the red curve is the approximation, the blue is hydrolyte, and the solid is downwelling, and the dash is upwelling. So omega naught is 0.01. That means there's very, very little multiple scattering, essentially a perfect solution. Omega naught is 0.1. Now that says there's a little bit of multiple scattering, but not too much. So the exact solution from hydrolyte and the single scattering solution are not too far off. But then as you get to bigger omega values, which are more typical of the ocean, then you have a lot of multiple scattering. So just looking at the solution for one order of scattering, you don't expect you to get very good values. And indeed you don't. Maybe right near the surface, but as you go down in the water, it can be off by orders of magnitude. So that's what happens with the single scattering approximation. And then Howard Gordon cooked up a scheme that says, take the single scattering approximation and you can massage it a bit and get what's called the quasi-single scattering approximation. And it's pretty subtle, and I'm not going to go into it, but it actually works very well. So here's now, for example, here's remote sensing reflectance computed by hydrolite in blue, the single scattering approximation in green, and the quasi-single scattering approximation in red. And you can see this quasi-single is pretty darn close to the exact solution, which has all orders of multiple scattering, and the single scattering is way off. And here's also a view of remote sensing reflectance versus omega naught. So low omega naught, they're all about the same. And then for larger omega naughts, they go very bad. So I'll just let you know that that quasi-single scattering thing exists. And that's how the atmospheric correction for the coastal zone color scanner was done. I mean, this was back in the days when, you know, we were barely out of the world of slide rules. And Howard came up with this quasi-single scattering approximation that could predict things like remote sensing reflectance, KD, and so forth. And that equation, very simple, was actually used to do the atmospheric correction for the CZCS instrument. And now, of course, this is all done, as we'll see Friday, with super fancy calculations. But this got the field working. So in Howard's older papers, and I was just looking at another paper Emmanuel sent me yesterday, and it just says, and the QSSA solution is, and writes it down. And so when you see that, and you have no idea what the QSSA solution is, go to the web book, the math is all there, you'll see it all derived, and you'll see the equations. But it's where you get things like remote sensing reflectance is proportional to BB over A plus BB. And then there's stuff out front that comes from the solution, and that's from the quasi-single scattering approximation. Okay. Yeah, you have to use numerical techniques to solve the full equation. We'll do that with hydrolite starting this afternoon. Next week, we'll talk about Monte Carlo techniques that can solve the full equation, and including the vector one. So you'll see a little bit more of that next week. So that's it for radiative transfer theory. Now, I strongly suggest that you do a vacation to Greenland, but go to East Greenland. There's way too many people living in West Greenland. So the coast of Greenland from north to south is basically the distance from Canada to Mexico. And there's like 50,000 people living on that coast in West Greenland. So it's really crowded. But East Greenland, there's only like 3,000 people living between Canada and Mexico along the coast. And they're all sprinkled around in a few little Inuit villages. And there's only one that has, I think, about 2,000 people, which is the only thing you could call a town in East Greenland. The others are little villages with like 100 or maybe at most 200 people in it. So anyway, we went there. We kayaked from between two of these villages. One of them has a dirt airstrip. So we flew from Reykjavik, Iceland to Kulisuk, which has the dirt airstrip. And one trip, we paddled from Kulisuk about 80 or 90 miles to another little village called Sirmiligak. And then we hired a guy in a powerboat to take us back. And it was such a great trip. I went back and did it again in the other direction. So we started out, and we hired the guy in the powerboat to take us to Sirmiligak, and we kayaked back to Kulisuk. So utterly fabulous. Do watch out for polar bears if you're there. So I'm not a gun owner, but we did have shotguns with us in case polar bear got hungry. And it's scenery like this. The water's cold, so you try to keep the boat pointed upward. And that's my wife in the back there. Another thing I advise you to do is you always separate spouses in kayaks. So you're just asking for trouble if you mix a mated pair in the same double kayak. So anyway, that's her in the back there. And so not a lot of people do this trip. So when you pull ashore in one of these little villages, it's utter chaos. I mean, every kid in the town comes down to see what's going on, and sit in your boat and look through your gear and all of this. And so it's a lot of fun. And one of the places you pass between these two villages is an old World War II air base that was called Ikatak Air Base. And this was where airplanes were stationed on the east coast of Greenland that could fly out over part of the North Atlantic to do anti-submarine patrols to try to sink Nazi submarines. Well, all the fuel had to be brought in these 55-gallon drums. And they're literally like, square miles of rusty 50-gallon old fuel drums, because it was a one-way trip. You had a ship come in with a load of fuel, you put it in the airplanes, you threw the drums out back, and they're still there, as are all the hangars and everything, just rusting away. And the locals call these American flowers. So these things are just sprouting all over this whole big valley. So anyway, that's that. Great trip. Lots of other stories to tell, but I won't bore you with them. So it's now about 10 after 10. So take another break, and let's see, we have till noon here. The next lecture is not that long. Do we want to take like a 20-minute break and start at 10:30, and then we'll be done in plenty of time for lunch? Okay, sounds good. Okay, let's turn this guy off.